Okay, good afternoon. So my topic today is about use a bit different from there. This use ultra high performance fiber reinforced concrete called UHP-FRC, also called UHPC, for fast and sustainable repair of pavement. So currently the conventional concrete used for pavement, for repair, the concrete is the problem is durability issue. So we know concrete is a low strength, a very tensile strength, especially the one used for pavement repair or pavement construction is low strength. And concrete itself has porous microstructures, so very high permeability. So repeated repair can be very costly, time consuming. So we need a better way to repair this pavement. So the objective of the research is using a UHP-FRC. This is some new concrete materials because it has a very dense microstructure, very high strength, and durable and damage tolerant features. So we're using these materials to have a more sustainable and fast repair of pavement. So just quick introduction of UHP-FRC. And basically, for UHP-FRC was made by so-called high particle packing density. So to pack different particles, so we can reach a very high dense concrete, use less amount of water. So that way, can improve the defect that conventional concrete has. So we also add fibers there to increase the ductility. Usually those UHP-FRC is very highly flowable because the way to tailor the microstructure. One of the features is those UHP-FRC, this is the one we developed at UT Arlington about 5-6 years ago. We keep improving that. And the early strength is very high. One day can reach about 10 to 14 KSI in one day. Long term can reach ultimately to 30 KSI. You can see that its compressive property is high compression. Also, not only the strength but also ductility. Compared to plain concrete, it's very ductile. It's very hard to be crushed compared to conventional concrete. And its tensile capacity, or we do a tensile testing, direct tensile testing. And you can see there's ductility. It's not like conventional concrete. Once it reaches its tensile capacity, it failed immediately. And this will show a ductile behavior like steel. So its strength at the peak is 40 times compared to conventional concrete. It can be stretched a lot without failure. So these are photos compared to plain concrete and UHP-FRC after tension. So this is a comparison of former research, National Science Foundation research. We test the full-scale columns under extreme earthquake. So this is after about 5% story drift cyclically. So you can compare, you can see the damage tolerance capability of UHP-FRC. And there's almost no damage. Of course, there's some micro cracking there compared to reinforced concrete. This is designed based on ECI 318, the latest one. But still, not much damage compared to the conventional reinforced concrete. So a summary of the property of UHP-FRC. This is the conventional concrete, UHP-FRC. Compression strength is much higher, at least 5 to 6 times higher. Early strength is also very high compared to conventional concrete. Flexure strength, shear strength, permeability is very, very low. So that may make the UHP-FRC extremely durable. So the low permeability is one of the very important feature for durability of UHP-FRC. And also it prevent, if there's a reinforcing bar inside, it prevent the rebar from, or delayed corrosion process for rebars. And also very high cracking resistance. So this reason, the task ones, we further tailor UHP-FRC for pavement repair purposes. Because sometimes when we talk to people, the one we developed is using steel fibers that give the best performance. But some persons have concern about steel fibers. may sticking out of the road, somebody can step on that. So, or we want to reduce the cost. The costs can be very high compared to conventional concrete. So we use different fibers like this. They call ultra high molecular weight polyethylene fiber. So this has an equivalent tensile strength compared to steel fiber. The same diameter. We use this kind of fibers to replace steel. Of course, we have to change the mix design and slightly. Yeah. So there's some other different types of UHP-FRC we developed for other purposes, like pavement repair, and also reduce the cost. For example, we reduce some of the components by using slag cement. So this is the task one. Task two is to developing a efficient pavement repair procedure utilizing UHP-FRC's unique characteristic. So this is a conventional way to repair concrete pavement, saw cut the damaged part and put a dowel bar, sometimes tie bar there. For continuous reinforced pavement, they sometimes have to splice the bar with the original existing rebar. So this is a conventional way to do that. So the proposed method for our research is this. This is an existing concrete pavement. So we saw cut and whatever the region needs to be repaired. And then there's a precast patch. So the precast can be UHP-FRC. If this region is under very high stress or critical, we use UHP-FRC as a high performance. Or RC or PC with HPC, for example. So this patch and including this saw-cut region will be roughened, surface will be roughened, and no dowel bars used. So this roughened surface will provide very high shear resistance to prevent the faulting between the existing one and new one. So on site, the casting work for UHP-FRC is very minimal. So you put a patch here and then cast UHPC on site, probably 2 inches enough. And depends on how fast you want the strength to grow. If you want, for example, 4 hours, reach 2,500 PSI, and you may need some curing here, on-site curing here to get that strength quickly. So to prove this concept, we did some testing in the lab using a they call slant shear testing. This is one of the most commonly used method to check the shear strength between different interface between different materials. So basically, this is a bottom part representing the existing concrete, the upper one representing the new concrete. So the loading applied on top. From mechanics, we know that there will be shear force. At the same time, there is a force perpendicular to the surface that will create a friction. So the friction will counteract some of the shear force. So this doesn't represent the most realistic condition, but it gives a very quick way to get the understanding of the shear strength. So this is the test setup at our lab. For conventional concrete, so what we do is follow procedure. Then this is saw-cut smooth surface, and drill the hole by drilling the hole and put the reinforced bar inside and using epoxy to grout it. That's the typical way they do that. And we have shrinkage here, so we can measure the deformation with strain or indirectly stress the rebar, and then cast the top part. So I will just show some result for the plain concrete. There are 2 specimens here, and they have similar performance. This is the applied loading versus the deformation along the shear plane. And this graph shows a strain gauge data on this dowel bar. So you can see that this is the peak force, and the peak force, or before the peak force, the strain reinforcement is extremely small. It's very small. So if we back calculate that one using the strain we measured, we found that the force taken by reinforcing bar is only 1.2 kips, while the peak force is about 50 something, 55 kips. So this tells us that the dowel bar there doesn't actually help too much to resist the force. It only happened after the slip occurred. So the most resistance coming from concrete itself, not the dowel bar. So the second testing this. So we don't use dowel bar here, and we roughen the surface and using a pneumatic surface scaler. And roughly to the CHP5, there's a profile provided by International Concrete Repair Institute. So roughly equal to this surface, and no dowel bars, then cast UHP-FRC on top. So after 1 day, we test the specimen. First, the concrete strength reached for 11 KSI. This is commonly reached for UHP-FRC. Then this does not fail until 81 keeps. The previous one was conventional concrete with dowel bar there failed at 55 keeps. So this tells us if we roughen the surface to some extent and provide a very strong repair concrete, and it can provide even higher resistance to the faulting or settlement. And it's 50% higher. So in this case, we don't really need the dowel bar there to provide resistance. So all this roughness can be done before cast concrete, as I mentioned. So the ongoing testing, so moving towards more realistic testing that this representing that is taking concrete, and that is the concrete patch, precast patch I mentioned in other slides. And we can cast UHP-FRC, very small part of UHP-FRC after this, and do kind of like testing like a well loading, the actual well loading to the testing to prove the concept. So for implementation, currently we're talking with the city of Bedford in Texas, in North Texas, and Lowfield Airport in Dallas, about using this concept, and with some communications. Hopefully then we can find a spot to prove this concept. A summary, the impact of this research, if this, based on what I presented, we can do a very fast, durable pavement repair, especially for a region that can be not needs constant repair, or the taxiway for airport. This can provide a better cost savings for short-term and long-term transportation infrastructures. And this research can be also used for other structures in the future, like marine, nuclear, or other type of infrastructure repair. It's the same concept, same idea. So this concludes my presentation. Thank you.